So hello everyone again. Welcome back to week 9 of the Quantum Device Engineering course. Hopefully you've all enjoyed last week's lecture. I got some good feedback from it. Unfortunately, just due to commitments and being really busy this week, I'm unable to do an in-person session. But please send me all of your messages that you have to Teams. I've only had like 2 messages in total on Teams. It's a very easy way to get in contact with me. I'm always on my Teams, so send me questions. I'm happy to answer them. But just going to do another brief tutorial on this week integrated deterministic photon sources. So last week we talked about integrated probabilistic photon sources, such as SPDC and four-wave mixing. It's four-wave mixing specifically last week. Yeah, and this week it's kind of one approach on how they've integrated a deterministic photon source onto a chip and all of the advantages that come along with that. Okay, so what is a deterministic single photon source? Hopefully you're pretty familiar with what this is by now, but it is a device that produces on-demand single photons with a high level of predictability and control. And examples of this are quantum dots, trapped ions / atoms, NV centers in diamond, rare earth ions, and also molecules. And the focus of the paper today is molecular emitters of single photons. So, what is a molecular single photon source? Well, essentially, it's a cyclic molecule, such as these ones down here at the bottom of the page, that are excited by a pump light and emit a single photon based on the electron energy level structure of that molecule. Okay? And the advantages of molecules, one of them is that you get a really strong desired emission at a frequency or wavelength known as the zero phonon line. So that's known as here. Okay, and zero phonon basically just means that it is the energy level that you are exciting. It is just like the primary energy level that you're exciting. However, if you look at this diagram here, which again is intensity of emitted photons versus wavelength, you can see that there's some other secondary little peaks here, and these are like basically due to phonons interacting with the energy level structure of the molecules. So phonons just like vibrations, basically, imparting energy on the molecules, and this energy will broaden the energy levels of your molecule. And as this is indicated by these kind of grey bands here in the energy level structure. So the grey band indicates that the energy level could change from this black line, which is the primary zero phonon line, to these kind of broader areas here. And this broadening of the energy basically means that your excitation, and so your emission of photons, the frequency at which this happens just changes slightly. And that's shown by these peaks in emission at unwanted frequencies. So a small disadvantage of molecular sources is that you do get these unwanted emissions. But these can be improved by things like cavities and things like that. So maybe if you were thinking of writing a report on this, you could think about how maybe you could suppress these kind of sidebands and increase the intensity of this zero phonon line. A really nice advantage of molecules is that they're very easy to manufacture. We've kind of got the manufacturing process down on molecules, and you can tune the wavelength of emission of photons by just altering your molecular structure here. So this is the basically emission wavelength of some different molecules. This is taken from Alex's slides, so I'd recommend having a look at those. But you can see as you kind of add extra rings to this cyclic structure, you get an altering of the wavelength of your emission. And so this kind of gives us a nice easy tool to tune the emission of our photons. So we can basically easily tune the emission wavelength of our photons. And another nice advantage of molecules is that, as we'll see in this paper, you can quite easily integrate these molecules onto photonic structures. And I'm comparing this to other deterministic sources like NV centers. NV centers, they have been placed on waveguides, but the way they do it is you kind of have one chance to place them, and if you want to kind of replace where these diamonds sit in your photonic structure, you would have to kind of completely wash the substrate and start again and then redeposit them. As you'll see in this paper, we can quite nicely kind of like rejig the positions of these molecules. However, again, as we'll see from the paper, it is still it's still a probability of where these molecules will end. There's no way that I know of. There may be somewhere in the literature, but I haven't seen it. There's no way of like deterministically firing a molecule at a specific spot on a waveguide. So as you'll see from this paper, the position is not exactly as we'd want it, but it's better than things like NV centers in terms of positioning. And a disadvantage of molecular photon sources, as with a lot of deterministic single photon sources, the light that is emitted in all directions. So how could we overcome this? Well, that's what this paper basically demonstrates. Okay, we could, if we wanted to create nice directionality of our light, we could couple the molecule to a waveguide, and that's what this paper is all about. It's basically coupling of a molecular deterministic single photon source to a waveguide. Okay, so the first thing I'm going to go through is how they actually make the chip and how they position these molecules in proximity to these waveguides. So they start off with this material structure of fused silica on top of titanium dioxide. They then use a lithography process to define a waveguide like this. This looks like any other waveguide, and the light will be guided in this kind of central region here. They then use a process called wafer bonding, and it's just what it sounds like. You just get two wafers and you stick them on top of each other, and you fuse them together with some sort of either adhesive or some kind of natural like van der Waals type force between them. So you stick them on top of each other, and as this diagram kind of shows, this creates this nice like well here. Okay, this nice empty air gap between the TiO2 and the fused silica above it. And then what they do is they have molten anthracene, AC, which is kind of signified by this green coloured here, and they use this as a matrix within which to dope dibenzoterylene inside, so DBT. DBT is the molecule that we're going to use as our single photon emitter, and by basically what they do is when you heat up anthracene, it becomes liquid, and you can kind of flow it through these wells above the TiO2 structure. Then you cool it down and it will solidify, and this solidification will trap these DBT molecules within the AC matrix, and they will be kind of stuck in place. And there is a chance, as you're reflowing, that these DBT molecules sit in close enough proximity to your waveguide that you're putting light through, allowing it to couple into the waveguide. And then what they do is they pump light into this DBT molecule from above with a strong pump laser. So they kind of fire down, so if the waveguide is going that way, they fire down onto it. And then they also send a probe light through the waveguide, so they put it in through a grating coupler at one side, and then it comes out the grating coupler on the other side. Okay, so the pump light comes from above, and the probe line propagates through the waveguide that we've defined in our TiO2 material. Okay, and the nice thing about this process is that if you flowed this AC and the DBT molecule didn't sit somewhere that we wanted it to sit, we could just heat it back up and we could reflow it and move the molecules around, and do this multiple times until we have good positioning of our DBT molecules on top of a waveguide. And this is the advantage over the NV center that I was talking about, in that you can reposition it. Okay, hopefully that makes sense. You can send me questions on Teams if you want to know any more about this. So this is kind of like what their structure looks like from above, from the supplementary. So you can see this is the grating coupler here, and this is another grating coupler here, and this is how they put the probe light into the waveguide. So you put a laser into this, you shine a laser at this, sorry, it couples into this waveguide, travels out here, and then would come out of this other grating coupler on the other side. And they've got a few different shapes of grating coupler and waveguide. And you can kind of see these light coloured bits here. So where it's light coloured is kind of where they would flow in the DBT. And where these dark bits are just electrodes that they use to kind of try and do stark shift of their molecules with. Okay. So, what does this do? Like, what's happening inside these waveguides? Well, if you imagine just like the simplest case, so you've got just a waveguide here, and you've got a probe light again coupled in through these waveguides. You've got a probe light, a weak probe, travelling from left to right through this waveguide. If you had no molecule in proximity to this waveguide, 100% or 100% of the light that's coupled into the waveguide theoretically should travel through the waveguide and then be detected out on the other grating coupler. There's obviously going to be, in real life, there's going to be losses and stuff with these grating couplers, but yeah, you would count this as 100% transmission of your probe light through the waveguide. And now, imagine if our DBT molecule sat on top of the waveguide here. Well, what can happen is that this weak probe beam, if it's on resonance with the energy levels of the DBT molecule, it'll travel down this waveguide, it'll then be absorbed by this DBT molecule, which will then re-emit light in all directions. But because our DBT molecule is strongly coupled to our waveguide, you get guiding of the light. Okay? And so you now have two scenarios. Your light will either be transmitted in the same direction as your probe beam, or it will be kind of like reflected back in the direction that the probe beam came from. So like kind of 50-50 splitting of your light in the two directions that the waveguide travels. Okay? And so if you now think about the transmission, how it's changed here. Okay? Here we had 100% transmission through the waveguide, but here, basically 50% of our light that would have normally travelled through here will be sent in the opposite direction back towards our probe light. And so if you were measuring the transmission here at this side, you would notice that you'd get a dip in the total transmission of light through the waveguide. And if you measured the reflections here, compared to this example, you would see a peak in the reflected light. And that's exactly what this first graph shows. Okay, so this green graph here is transmission, so again, in the direction of the probe light, and this red graph here is reflection, so again, in the direction that the probe beam came from, so kind of back towards your source. And this dotted line here is just showing you, where's my mouse? There it is. This dotted line here is just showing you that you get a dip in the transmission associated with a nice peak in the reflection. Okay, and again that's caused by this process here. So that kind of explains this green graph here. Okay, so this was the simplest scenario, and this is where we have no pump beam shining from above. We just have a probe beam. Okay, so now imagine we shine a strong pump beam down on top of the molecule, whilst we also put a weak probe beam through the waveguide, so they're coming kind of perpendicular to each other. Well, because our pump beam is strong in comparison to our probe beam, the pump beam will preferentially excite the DBT molecule. And if the two are on resonance, we'll basically get complete saturation of the energy levels. So the energy levels will be excited like fully by the pump beam. And so, because this is completely saturated by the pump beam, our probe beam will essentially just pass straight through this waveguide and not couple at all into the DBT molecule. Okay, and so essentially, by putting this strong pump beam in, we've made the DBT molecule transparent for the probe beam. Okay, we'll still get transmission and reflection, but we will also be able to measure the probe beam out here. Okay? And this explains this figure in the diagram. Okay? So this graph here is at 3 different pump strengths. So the light that's being basically making this transparent or not transparent. Okay? And this here is the transparency, the transmission of the probe beam. Okay, so it's the transmission of the probe beam. And when we have, this here is the weakest pump light. This is the kind of middle strength of pump light, and this is the kind of really strong pump light. And you can see that the transmission here dips. You get a nice dip in the transmission, and this dip is the kind of first scenario that I showed you. This is the scenario where your probe light is exciting your DBT molecule, and then you get a splitting of the light in the 2 directions. Okay, so that's what this dip is. And then as we increase the power of the pump light, you can see the transmission basically goes to 100%. And this increase to 100% essentially means that the DBT molecule is transparent to your probe light, as I explained here. So that's just this process here. So this just shows you that you're turning on and off the transparency by varying the power of the pump light, which is the light coming from above. Okay, so strong pump beam, transmission reflection, and you get the weak probe going straight through, 100% transmission. Weak pump beam, you get the dip in transmission, which is caused by the DBT molecule being absorbed and then re-emitting as a result of the probe beam. Okay, so you can see the turning on and off of this transparency. Hopefully that's clear. And again, send me a message if it's not. Okay, so there's an interesting thing that you can notice from this graph. If you follow kind of like all the places where there's peaks here and there's dips here, there are some scenarios where you kind of get a dip in the transmission without an associated peak in the reflection. Okay? And what this is caused by is an effect called Rayleigh scattering. I don't know if it's Rayleigh or Rayleigh, but I'm going to say Rayleigh scattering. Okay? And basically Rayleigh scattering can cause a dip in your intensity. And so what happens? You basically have to imagine co-propagating probe beams travelling through this waveguide. And the DBT molecule, even when, so if you had a strong pump light, okay, and so this is not being, your probe light is not being absorbed by your DBT molecule. Although it's not being absorbed by the molecule, you can sometimes still get scattering of this light by your DBT molecule, okay? And this Rayleigh scattering essentially causes a pi phase shift to be induced between your co-propagating beams. Okay? And because you have a pi phase shift, as you can kind of see here, your 2 beams are completely out of phase, and you'll get destructive interference of the 2 beams. Okay? And you'll get destructive interference because your 2 beams are nice and tightly confined by your waveguide. Okay, so they're co-propagating kind of, they're completely co-propagating, confined by your refractive index contrast of your waveguide. Okay, and again, this is just to explain some of these dips in transmission. Okay, hopefully that makes sense. Again, so many questions. So one final note that I thought was interesting about these transmission dips is that if you look closely, this resonance here, where you kind of get a dip, it's not disappearing completely. Okay, it's actually shifting to frequency. So in all of these powers of pump beam, you can actually see a kind of a local minima or a resonance here. Okay, and you can see that this resonance for the 3 different powers is shifting to a lower resonant frequency. Okay. And this is because as you increase the power of your pump beam, you essentially increase the electric field that the molecule is feeling. Okay, And this can do a process called AC Stark shifting. Okay, DC Stark shifting you might have heard of more, but AC Stark shifting is essentially you put an electric field over a single photon emitter, and you will get a kind of spreading out of the energy levels, or a shifting of the energy levels. And this shifting of the energy levels will change your resonant frequency, and that will cause the frequency of this dip here in transmission, so the frequency at which light is strongly absorbed by the probe light is strongly absorbed by the molecule, will cause this to shift to lower frequencies. And hopefully that makes sense. Increasing power causes Stark shift, causes a shift in your energy levels, changes the resonant frequency of your molecule slightly, and that's what causes these local minima to kind of decrease in frequency here, indicated by these X's. So there's a bit in the paper that I think is actually quite confusing, and I actually had to go and talk to Alex about it because I was I was a bit lost, to be honest. And they talk about amplification a lot, okay? And they display it in these three graphs here. So you can see from this transmission graph here, you can see that the transmission goes up to 106%, so you're getting over 100% transmission of your probe beam. And this graph here further shows that. This coherent amplification, you can see that at a pump Rabi frequency of over 40, you kind of get the you basically get coherent amplification is turning on. And you can also see here where the transmission at high pump powers increases to over 100%. And it's a bit weird. It seems like an unusual point of the paper, and so you'd expect them to kind of tell you why this is happening, but actually nowhere in the paper did they suggest a mechanism for this, even in the supplementary, which I had to read through. So talking to Alex, we kind of looked at some other papers doing similar things, actually a free space experiment, and they also saw a little bit of amplification, not to the same amount, but a little bit of amplification, and they put it down to a four-wave mixing process facilitated by the presence of the DBT molecule. Okay, so you'll basically get four-wave mixing of your probe and your pump beam, facilitated by the DBT molecule, that will cause the creation of a signal and idler photon, just a normal four-wave mixing process. And these signal and idler photons will propagate down the waveguide. Okay, and normally you wouldn't really detect this pump beam in the transmission of the waveguide, but this four-wave mixing process basically will cause further photons created by this process to travel in the direction of the probe beam, and the presence of more photons will be detected as more clicks on your photodiode at the end of the experiment, and that will be seen as an amplification. It'll be seen as an increase in the signal, and so the amplification that they measure. And in free space, I mentioned that the process, the free space experiment, where they talked about this four-wave mixing process, had a weaker four-wave mixing effect than this experiment. And that's because one of the big advantages that I keep harping on about in integrated photonics is that you have really nice tight confinement of your mode, of your light to these really small waveguides. And it's quite easy to confine light to these waveguides in integrated experiments. And this integration and tight confinement of these two co-propagating modes, the pump and the probe beam, allows four-wave mixing to happen, and it'd be much less likely for this to happen in a free space experiment, because it's much harder to confine light in a bulk experiment. Okay, and it's also much harder to confine your emitted signal from the four-wave mixing process in a free space experiment. So that might, partially explain why the effect seen in this paper was a bit bigger than the effect seen in that free space paper. So again, the paper doesn't really go into it, but I think it's interesting. This amplification is caused by a four-wave mixing process facilitated by the DBT molecule and the tight confinement of your light to this waveguide, and then the subsequent tight confinement of your emitted signal and idler photons by this waveguide. Okay, and again, this slide should hopefully explain that. And I would recommend talking to Alex about this one if you have more questions about it, because it's really interesting, and he's very much the expert on molecules. He does love talking about molecules. Okay, and the final graph I want to go through, I'm hoping, is one that you're all very familiar with at this point. I've been through it, I think this is the third week in a row I've showed you this graph, but this is for this experiment, obviously. So I'll give you a few seconds to think, what does this dip in G2 that dips down to 0, what does this tell us? What does this tell us about our source? And a little clue, this is the experiment they use for this G2 experiment. Well, if you answered that this dip to 0 indicates that we have a very pure single photon source with very little bunching of our photons, you would be completely correct. Again, the experiment is like this. You have your single photon source over here, and then you send it to a 50-50 beam splitter, so the photons have a 50-50 choice when they hit this beam splitter of either hitting detector A or detector B. And if you have a single photon source, that means that each photon is sent individually and none of them will overlap, none of them will be sent at the same time. And if you have no photons hitting this 50-50 beam splitter at the same time, if you look at detector A and detector B at the same time, so this time delay t at 0 time delay between the detector A and detector B, you should never see a click in detector A and detector B at the same time if you have a pure single photon source, because you can't split a single photon into two here. Okay, and so this dip here to 0 means that we basically never see detector A and detector B clicking at the same time. But of course, you already knew that. I think that's everything. In summary, what's really cool about this paper is that we essentially have a way of turning on and off the transparency of a single, not transparency, sorry, you have a way of turning on and off a single photon source. Okay, so you can turn on and off a single photon source by the presence of a strong pump beam. Okay, so you have, in essence, a nice deterministic, controllable source. Okay, and by kind of reflowing that AC material and doping it with our DBT molecule, we can position single photon emitters in close proximity to a waveguide. And this close proximity to the waveguide allows us to strongly couple the output light of our single photon emitter into our waveguide. Yeah, and it allows us to basically have a nice, tightly confined, usable, deterministic single photon source that we can then use for integrated photonics experiments. It's a really cool demonstration. Yeah, and I hope you enjoyed it. Again, send me lots of questions, send Alex lots of questions, and I will hopefully see you in person next week.